All right, section 12. To start, let's go through the labs that I think are like important slash less important for this section. So section 12, we're going to be going through a few different distributions. First, these first 6, probability mass function to cumulative distribution function. The idea of these, I'm going to go through in just a sec, but for these labs is more the idea of what a probability mass function, what a probability density function, and what a cumulative distribution function is. Once you get the ideas of that, there are some other things sprinkled throughout these labs, so good to just take a read. But in terms of like how important it is, I think just understanding what the functions are, like what these phrases mean, that's good enough. Bernoulli and binomial distribution, honestly, they are my favorite distributions in all of statistics, but not important for data science. So I'm going to talk about it maybe a little bit too much today, but not important in the larger context of data science. These, though, from normal distribution, standard normal distribution, super important. So if there's one thing that you want to focus on, it's these 4 labs. And then the thing is, to understand these labs, you got to understand a little bit of like probability, mass function, density function, and the cumulative function. So that's why that's like a good primer to that. But the main thing to take away, I think, from this section is the normal distribution labs, as well as the ones right after that, statistical testing. However, I think that the number of labs in this section is a lot. So I'm actually going to stop today right before one sample z-test, and I'm actually going to start next section with that. So basically today I'll only talk to I'll introduce what a z-score is, and that'll end today's session. And then on Thursday, we'll start with that and then go through section 13, which as you can see is a lot shorter. So just so you know, if you're looking for that stuff, that will come on Thursday. Any questions about the lab structure for this section? Cool. Yeah, so overall, I think the very important ones to understand are the normal distribution, as well as understanding what a z-score means, but not including testing yet, because testing we'll talk about on Thursday. And you just need to know like the first 6 labs for context. All right, let's get started. Section 12 is on statistical distributions. We're going to talk about this first thing is expected value and variance, and we'll go into that right after this. The long phrases I was saying, probability mass function, probability distribution function, density function, sorry, and then cumulative distribution function. These are all general ways to display probability graphically. I'll go through that as well. As I said, section 3, Bernoulli and binomial distributions, a little bit less important, but actually very, very interesting. Why I say it's also another thing why it's less important, because it brings back permutations and combinations a little bit. I have never gotten an interview question on this. Very few people, I think in data science, need to know what it is, but I'll just talk about it just so you are aware of how it works. Normal distributions, and I'll start introducing the concepts for a one sample z-test. Cool? And as usual, any questions, feel free to interrupt me. So to start, what's an expected value and what's a variance? These math formulas I'll break down in a little bit, but basically every random variable has an expected value and a variance. To backtrack one more step, what is a random variable? Random variable is just something that, you know, has multiple possible outcomes. It's something that you want to find the probability of. So for example, rolling a dice would give you a random variable because it can give you 1 through 6 and it has an expected value and a variance. So what I mean by what is the expected value of a dice roll would be the average of your dice rolls, basically. And so to break down this formula, the expected value of any random variable x, x being the random variable, is the sum of the probability of each little x, and each little x is a possible outcome multiplied by itself. And so let's use the context of a dice roll. Dice roll, you can get 1 through 6, and each of your, each outcome has a 1 out of 6 probability of occurring. And so therefore, we would just take 1 times 1 out of 6, 2 times 1 out of 6, 3 times 1 out of 6, add them all up together, and you end up at 3.5. So if you average out all of the possible dice rolls that you can get, average them out, that would be an expected value of 3.5. So that's just saying that if you were to roll your dice, a bunch, on average, if you like sum up and take the average of your dice rolls, it should come up to about 3.5. And if you're doing an infinite number of experiments, the average of that is 3.5. Questions on that?
Yeah, can you explain the 3.5 part? It's like...
Oh, yeah. So when you roll the dice, there are 6 possible outcomes, right? So that you can get a 1, 2, 3, 4, 5, or 6. Actually, let me whiteboard this. Let's see if I can do this. Do you guys see like the blank screen now? All right, cool. So you have a dice roll that can do, why is it yellow? Let's do that. Possible outcomes are 1, 2, 3, 4, 5, and 6. And so each of these has a 1 out of 6 chance of occurring, right? And so in this formula, if you want to sum the probability of xi times xi, and each xi is basically each possible outcome, that means we're taking the sum of this multiplied by this. So in that case, putting it together, it would be 1 times 1 out of 6 plus 2 times 1 out of 6 plus blah, 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 all the way to 6 times 1 out of 6. And when you do the math and like add it up together, actually it simplifies to 1 plus 2 plus 3 plus all the way to plus 6 divided by 6. And that gives you 3.5. Does that make sense? Yeah. And then on top of that, you also have the variance. The variance, which actually I won't go through this on this whiteboard, but let me reshare the slides. With variance, which will become more, it's more, what's the word? More relevant for other distributions, so we won't talk about it yet. But to find the variance, which is how much a random variable can vary, or like the range of their values and how often and how widespread their values are, this is the formula. And basically very similarly, instead of multiplying the probability by the number itself, you're multiplying it by its deviation from the expected value. That's a little bit less important. But what I'm getting at here is for specific name distributions. And today we're going to be talking about the Bernoulli, binomial, and the normal distributions. There are often already set formulas for expected value and variance so that you don't have to calculate this. I do think in the labs you will be asked to calculate a couple of these, but if you just plug it into the formulas, it should work. Questions?
Makes sense pretty much, Yish, but can you just explain once more, what does the expected value tell you? Like, I'm sure it's not an average, but I just wanted to just understand, okay, once I have the expected value, that, because it's taking all of the different options, right, into consideration, but then now it's saying it's expected. So it's a little bit confusing to say, okay, well, is this 3.5, and do I expect to get this? Or how do you know you're expected to get this? Is it based on infinite rolls? Can you just explain that briefly?
That's a really, really good point, because I said that the expected value is a 3.5, and you can't possibly roll a 3.5
right on
a dice. It actually is much closer to an average. So that, yeah,
Okay.
it's actually
Gotcha.
much closer to an average. So like for a dice roll, it's a little bit less obvious because for a dice roll, each number has the same probability of occurring.
Right.
We'll see later in different distributions that if you have a probability density function, which I will get to, if you have a probability density function that isn't a flat line, because a dice roll has a flat line for a PDF, if you have a different distribution, you'll see that the expected value actually tends to be closer to where it peaks.
Gotcha. Okay.
It's just that like the dice roll is a uniform variable, which if anyone's interested, a uniform variable, that stuff actually lives in the appendix under more distributions. There are other distributions that exist. I will say not super relevant, but these are other distributions that exist that if you want to read about, dice roll is an example of a uniform distribution.
Got it. Yeah, no, good. Thank you.
Awesome. Anything else? Cool. All right, so let's get into those definition words that I was saying a bunch. So first we have probability mass function. And a probability mass function, which I always just say PMF, it associates probabilities with discrete random variables. And by discrete, I mean by it's a known number of possible outcomes. So here's a PDF that a PMF, sorry. It's a PMF that I just took off the labs, and we can maybe like make up an example for what this is. So maybe this is, you have a weighted 5-sided dice. So weighted die is basically like not each side has an equal probability of showing up. But in this weighted 5-sided die, you have like maybe like think what this is 31% chance, the probability of 0.31 to get 1 and 2. You have like a 0.15 probability of getting a 3 and a 5, and a 0.8 of rolling a 4. And this probability mass function just shows you the probability of getting each outcome. Very, very useful because at a single glance, you can just say the probabilities of getting each outcome. If you want to do like more complicated probabilities, like what is the probability of rolling an odd number, an even number, very easy to see and add up. Probability mass functions can be written out like, for example, in this case, it seems like 1 and 2 have a probability of 0.31. It can be written out individually. It could be rule-based. You can also see later when we talk about the Bernoulli and binomial distribution, you can write it out as mathematical formulas, but those are for very specific examples. Question of that. So main thing to take away, PMF just shows you the probability distribution. It just shows you the probability of getting each discrete outcome.
This is just a quick question. Can you, it might be a crazy question, I don't know, but can you use this in reverse, basically? Can you use this to say, oh, I want to use this particular function to distribute values in a particular way? Or is it only to look at data that you already have or options that you already have? Can you use this to make things happen in this distribution? That's
a really interesting question. So I would say that there is no order of operations in this case. For this is just a visualization of something that you have. So let's say if you want to create a distribution that has like, for example, probability is 2 times whatever the number is, you can create that distribution as well.
Got it.
One last thing to note is that each of these bars must add up to 1. Yeah, that's one quick thing.
All right.
Cool. Now, after probability mass function, which is discrete, we have I always say the wrong thing. I need to double check if it's mass or. So mass function and then density function. So this one should be probability density function, which I'm going to edit right now because I'm going to get confused by this. So this is a probability density function. And the only difference between a density function and a mass function is that, you guys still see the slide? All right. The only difference between the two is that density function, PDF, is for a continuous variable. And we haven't really talked about continuous variables yet, but a continuous variable is basically something where you can't you don't have a set number of possible outcomes. So in this case, which is also taken from the labs, this is the probability density function of the temperature on June 1st in New York City. And this is basically saying that, all right, let's start here. Let's start on the right side. 13% of the time you'll observe a temperature between 79.3 and 80.8. That's because this middle bar has that range of 79.3 and 80.8. And this bar is at about 13%. Yeah, any questions about this?
Well, just a comment, pretty much, is it safe to say that for density functions, there's constantly an output that you're measuring, as opposed to the mass function where it's just, okay, this is one time, second time, third time. Is that safe to say or no?
That's a good point. Not exactly that you keep measuring things. It's just that in a continuous variable, for example, you have 79.3 and 80.8, but in between these two numbers, there's an infinite number of points in between those numbers. So for example, if you're looking for, let's say, a temperature between 79.3 and let's see, what's a good example to explain what I'm trying to get at here? Basically, like, you know how like you want to divide, let's say, I'm trying to, sorry, my brain has been like overworked today. In a continuous random variable, we can get into smaller and smaller increments. So we have 79.3, and it looks like we're using one decimal place here, but there's also a probability associated with like 79.31 or 79.30005. So there's an infinite number of points in this range of values, which is what makes it continuous. Does that make a little bit more sense?
It does. So for the mass function, that's not the case.
Exactly, because in this case, it literally can only be 1, 2, 3, 4, and 5. If you ask the probability of getting 3.5, it's 0.
Gotcha. All right.
Yeah. Where in this case, every value in this sample has, in this sample space, has a probability. More specifically, and they get more into it in the labs, the probability between 2 points is the area under this curve. Yeah, that's kind of like another phenomenon. And like, to get really into it, you have to get into integration and like calculus. But
Interesting.
And something that will also be pointed out in the labs is that you cannot find the probability of a singular point. Because the idea of this probability under a PDF is by like the area under the curve, you can't get a probability of just 80 degrees. Like if you ask for the probability of 80 degrees, it would be like asking what is the area of a single line.
Right.
And that would be 0.
Right.
This is where it gets a little like abstract and I guess very conceptual, a little philosophical, but
it's like you can't.
Yeah.
But it's like, I don't know. I'm just speaking out loud, just talking out loud. But it's tough to know the probability of something continuous if you don't have 2 reference points.
Exactly. Yeah, exactly. You need to have. So you'll see. I'm not sure if there are any questions, but like if anyone's ever taken like a statistics class, whenever you have a continuous variable, you always are asked to find the probability of a range and not a single point, because you can't find the area of just a single line.
Gotcha.
Yeah.
Okay.
The connection between like the probability and the area and why that is so, I won't go into it.
No worries. Thank you.
You're welcome. So we've talked about PMF and PDF, which are just 2 kinds of graphs that tell you the probability of things. One last one is a cumulative distribution function, which I know some places actually call the one for discrete and continuous ones different, but in our labs and also on Wikipedia, which I checked, CDF actually can refer to both discrete and continuous variables. And as the name suggests, it's a cumulative distribution. It's a cumulative function. So this is the CDF of a dice roll, and the probability for each, for getting like a single number of each, the probability of each outcome of a dice roll is roughly 0.18. And so you can see here that at each step, it goes up 0.18. So this mathematical notation basically is like, it shows the probability of your random variable, big X, being less than or equal to a certain number, small x. So in that case, let's say I just wanted to find the probability of getting 4 or less on a dice roll. You'll just look at the CDF, take a look here, and then trace it back to, what is this, 6 point, yeah, about 0.7, close to 0.7. That makes sense? So this is just like a different representation of probability. It is useful in some scenarios. So similarly here, if you want to find the probability or the proportion of the day that was cooler than 80 degrees, you would trace it back here to about 50%. So this is just like a different representation of probability. And oh, and one more thing to mention, the area under the graph does not sum to 1. Oh wait, it does not sum to 1. It does sum to 1. Does not sum to 1. Sorry, you guys. To be honest, these are things that I always confuse. So just good to know that they exist. Yeah, any questions before I move on? All right. Does it sum to 1? That's not an important fact. But all right, we're gonna move on to our first distribution, which is a Bernoulli distribution. A Bernoulli distribution is basically a one-trial binary outcome experiment. Examples are like flipping a coin, because you can either get heads or tails, 2 outcomes, and you're flipping a coin one time, and that is what a Bernoulli distribution is. Another example, maybe you have, you know, that game where you want to like throw a paper ball into a trash bin. Let's use that for this. So let's say you have a probability of 0.8 of making it into the bin or into the basket. That can be described using a Bernoulli variable. And so the notation for this, which you might see come up, is random variable x here. Tilde just means that it follows a Bernoulli distribution where p equals to 0.8. So we'll see this come up a little bit here and there, but for each distribution, you have a certain number of parameters that define it. In a Bernoulli distribution, the only parameter that defines it is the probability of a success. And so that, in that case, what we have under here is just p equals to 0.8. If we have a different experiment like flipping a coin, p will be equals to 0.5. And this is just a mathematical notation of like telling you what the distribution is. So in this case, the expected value is 0.8. So like literally the average value is 0.8 because you have a 0.2 chance of getting a 0 of failure and a 0.8 chance of getting a 1. And so if you just plug it into the formula, you'll get 0.8. The variance of this, again, if you plug into the same formula, you will get 0.16. Bernoulli distributions are, I would say, like it is the distribution with the least number of things that you're concerned about because it's literally binary outcome, one trial. So just to see here, these are the PMFs, and this is the PMF and the CDF of the distribution.
Why the CDF is showing as more than 1 as the total?
Yeah. So the area under the graph does not sum to 1 because this is cumulative. So cumulative, remember how like in this example, we're going up we're basically adding all the probabilities for whatever is below it. So for 4 here is the sum of the probabilities of getting 1, 2, 3, and 4. Therefore, in the CDF here, you're adding together the probability of getting a 1 with the probability of getting 0, which is 1. Yeah, that's actually something that's good to mention, that the CDF always ends at 1. Because it exhausts all the outcomes and ends at 1. And that's the full probability space. Cool. Yeah. This one study. Oh, yeah, go ahead.
Every time we are going to do CDF, it has, right, one side of the graph will always show at 1. It's going to stop at 1, correct?
Yeah, it will always start at 0 and end at 1.
Okay.
Yeah, yeah. I can tell you, like, in college, everything that I'm talking about in this study group, I did over like maybe 4 or 5 weeks of college. So there's a lot of stuff going on here, but I'm gonna try my best to like highlight what are the things that you need to know and what stuff are just like surface level, just know that it exists. So this is one of them. This is one of the know that it exists things. Same for the Bernoulli distribution. But like, I think you have to know some of these like concepts to understand the important stuff.
So then just for clarity, so if you had a situation where something was either yes or no, right?
Mm-hmm.
Did people do this or didn't they do this, right? Then you could use Bernoulli for that.
Yes, but you have to consider it as one group because there's only one trial. Did one person do this or not? Mm-hmm. Then it would be a Bernoulli distribution. If you have multiple people and they each have the decision of whether they do it or not, that is actually our next distribution. That's our
gotcha.
Yeah. So that's actually a really good way to distinguish between it. So Bernoulli is just a one trial binary outcome experiment. The next one is the binomial distribution. So the binomial distribution is a multi-trial binary outcome experiment. So again, you only have 2 possible outcomes, but the only addition here is multiple trials. And as you can see here, X follows a binomial distribution, BI is short for binomial. And here the parameters that it takes in that defines the distribution is not just probability of success, but also how many trials there are. And so if you're looking at like, the probability of like 10 people doing, whether 10 people will choose to bring an umbrella tomorrow. The probability of a single person bringing an umbrella is 0.8, but you want to find what's the probability of 3 people bringing an umbrella or 7 people bringing an umbrella. And I'll break this down in a little bit. So that's what this first line is. This second line looks very intense, but it's the formula for the PMF of a binomial distribution. So in this case, we are working with a binomial distribution that has 3 separate trials, each trial having a 0.8 chance of success. So in this case, let's say you're shooting basketballs and you have a 0.8 chance of making it. A situation that you would ask here is, what's the probability that I make 2 out of 3 of my shots? And to find the probability of making 2 out of 3, with the probability of 1 success being 0.8, if we look at this graph here, the probability of making 2 out of 3 of my shots is just under 0.4. And I'll break this equation down in a bit as well. And the probability of making all 3 of your shots is just about 0.5. Cool. And this is the CDF of it. It's literally just like stacking these bars on top of each other, so you end up at 1. Cool. Before I move on to like breaking down where this equation comes about, any questions?